So let's move on to discuss what it is that neurons actually do. We'll start by discussing what's happening while the neuron is at rest or being inhibited. This is referred to as the resting potential. The neuron is at rest, but it still has the potential to fire. So what is it the neurons do? Well, here's our working definition. The function of a neuron is to take in information from the environment or other neurons, integrate that information, and then send information along to other neurons. That's not really clear, so let's explicate a little bit. Our definition says that the neuron takes in information from the environment or other neurons. Let's leave out the environment for right now. We'll cover that in the next part of this unit. Let's just focus on neuron-to-neuron transmission. We also need to deal with this word information. Let's take that out and replace it with chemical messengers. So these chemical messengers are neurotransmitters such as dopamine, serotonin, and GABA. And then there's the word integrate. Well, that simply means to put together. Right? For example, both excitatory and inhibitory chemical messengers. So here's what we end up with. The function of a neuron is to take in the chemical messages that other neurons send it, add together the excitatory and inhibitory messages they carry, and pass on chemical messengers to other neurons if the excitation is great enough. And here's how it works. So we first have to go all the way back to 5th grade math and positive and negative numbers. So let's imagine that you're the treasurer of an organization, and to aid your bookkeeping, you keep a cash box. Right? In that box are 2 types of paper slips. Some represent debits, and others are negative numbers. Right? So they represent deposits and debits. The figure on the right shows the content of your treasury box with a net value of negative $5. Right? A potential donor has said that if your club can reach a net value of plus $5, she will provide a gift of $1,000. Therefore, adding a deposit slip of positive 2 nudges you towards that threshold value of positive 5. While adding a debit slip of negative 1 or subtracting a deposit slip of positive 1 pushes you away from threshold. Now let's take that concept and apply it to the neuron. The box represents a neuron that is a living cell. The debit slips represent molecules within the neuron that carry a negative electrical charge. In real neurons, these negatively charged proteins are mostly large protein structures that cannot move out of the neuron. We'll use the symbol negative P to refer to these proteins. So I think we need to zoom in a little bit here. So the deposit slips represent the positively charged ions, which can be either potassium or sodium. Potassium ions, which we will abbreviate as plus K, are concentrated inside the neuron. Sodium ions are concentrated outside of the neuron. Also concentrated outside the neuron are negatively charged chloride ions. Although the negative proteins always stay inside the neuron, the other 3 ions can pass through the wall or membrane of the cell. This is analogous to the treasury box. Adding and subtracting these ions will influence the net value or potential within the cell. And as with the treasury box, if that potential becomes positive enough and the threshold value is met, then a major event will occur. So we call this resting potential because it's a delicate balance of these 4 factors. Right? It creates what's called a resting potential inside the neuron. This means that when no information or no excitatory or inhibitory chemical messengers are picked up by the neuron, the factors at play are in equilibrium. These can be negatively charged proteins, the potassium ions, the sodium ions, and the negatively charged chloride ions. We should really call this a dynamic equilibrium because three major forces are at work here that produce the delicate balance. The first force is called electrostatic pressure, and it can best be described as opposites attract, meaning that areas of negative charge, like the negative 70 millivolt charge inside the neuron, attract positively charged ions like sodium. Conversely, charges that are alike repel each other. The negative 70 millivolt resting potential within the neuron repels the negatively charged chloride ions. The second force of this dynamic equilibrium is the tendency for molecules to move from areas of high concentration to areas of low concentration. Therefore, since the negatively charged chloride ions are concentrated outside of the neuron, they will tend to move into the cell where there are fewer chloride ions. The third factor is permeability, the ability of ions to pass through the cell membrane. So if we look at this model, we can consider these three forces and how they act on each type of ion. Notice first that the cell membrane of the neuron is drawn in a broken line. This is to represent the concept of permeability, that is, that ions can pass through this membrane. Chloride ions, the negative Cl, are concentrated outside the neuron, so they will tend to move through the membrane into the cell. However, negative chloride ions are negatively charged, so the negative charge inside the neuron will repel them. In fact, these two forces exactly balance each other out such that the negative chloride ions do not cross the cell membrane when the neuron is at its resting potential. Similarly, the two forces act in opposite directions for potassium. It tends to move out of the neuron because it's concentrated inside. But the negative charge inside tends to attract these positive ions back in. Therefore, for potassium, the concentration force is a little bit stronger than the electrostatic force, and therefore some potassium ions kind of leak out of the neuron while it's at resting potential. Notice that the sodium, right, and we can see both forces are acting on sodium ions to push them into the neuron. So why then is our negative 70 millivolt electrical potential not quickly drained? The answer is that the permeability of the membrane at rest is very low for sodium ions, and while it's relatively high for potassium and chloride. In other words, the sodium cannot get into the cell as easily as the potassium can get out, thus giving us a slightly negative charge. And remember, permeability doesn't mean that the cell membrane just has holes in it. Rather, embedded in the cell membrane are channels that are specific to each ion. We call these passive channels, and ions can pass freely through them. But each channel allows only one particular type of ion to pass through. There are a lot of passive channels for potassium, but very few for sodium. And therefore, the slight net force pushing a few potassium ions out of the many available channels, while there's only a small number of passive channels allowing the sodium in. And this very strong net force, right, is trying to push them in, but they can't get in because there are not a lot of channels. And this is where the third force helps maintain resting potential. This third force is called the sodium-potassium pump, and it does exactly that. It's a tiny mechanism that pumps those few escaping potassium ions back into the neuron and the few intruding sodium ions back out. All of these forces working together maintain our cell at resting potential until some outside force acts upon it. And that'll be the topic of our next lecture.